Welcome to the third lesson of Chapter 1. Today, we will discuss about the continuity of graphs involving limits. How do we know the function is continuous at a point? In order for a graph of y equals f of x to be continuous at point A, it must meet all three requirements. The limit as x approaches A is defined. The function value when x equals A is defined, and the limit value at A has to equals the function value at A. With just one requirement unfulfilled, the graph will be discontinuous at point A. Not knowing how to graph of the piecewise function, y equals 4x squared minus 6x when x is smaller than 0, and y equals x cubed minus 2x squared minus x minus 3 when x is greater or equal to 0 looks like. Can we know whether it is continuous at x equals 0? Yes, by determining whether it follows the rules of continuity or not. First, I'll find the limit of the function when x approaches 0. Using the formula in the interval that is greater than 0, I find the right-handed limit equals negative 3. Using the formula in the interval that is smaller than 0, I find that the left-handed limit equals negative 3. Since two one-sided limits are the same, the ordinary limit at 0 is defined and equals to negative 3. Now I'll look for the value of the function when x equals 0. Substitute 0 into the formula used in the interval that contains x equals 0. That's going to be x cubed minus 2x squared minus x minus 3 when x is greater or equals to 0. I find that x equals 0, y would equals negative 3. So the function values is equal to the limit value at 0, which equals negative 3. Hence, the graph of the piecewise function is continuous at x equals 3. Removable discontinuity at point A is where you have a hole at point A. It's where your limit at point A exists, but not the function value at point A. In contrast, a jump discontinuity at A is where your function is either undefined or defined, but the limit at point A is undefined for sure, because the right-handed limit is not equal to the left-handed limit. It is called jump discontinuity because just by looking at the graph suddenly jumps at point A, creating a significant gap that looks like a step. Lastly, an infinite discontinuity occurs when the graph has at least one of the two one-sided limits at A that do not exist in R. That means that one or both one-sided limits can equal unreal value, like infinities. This can involve asymptotes, where either your left or right-handed limit can go to positive or negative infinity.